So let's consider what's actually happening in our paper chromatography. So as an example here, I've got 4 standards. So that's leucine, glycine, glutamine, lysine, and then we have our hydrolyzed dipeptide, so with 2 separated amino acids, and we don't know the identity of them yet. The stationary phase, that is the paper, is actually water. That is water bound to the cellulose molecules on the paper. Our mobile phase is butanol acetic acid water. So our stationary phase is very polar, and our mobile phase is relatively non-polar compared to the stationary phase. Now, as the mobile phase, as we put the paper in the tank, the mobile phase will start moving up the paper, and very soon it'll hit these spots of sample. The molecules in the sample will then partition between staying bound to the stationary phase, to the water, or going into the mobile phase and moving a little way up the paper. And the chemical nature of these side chains will determine the relative affinities of these molecules for the stationary phase or for the mobile phase. So let's have a look at them. So we have leucine, which is a non-polar aliphatic amino acid. We have glycine, which is still non-polar, but you see it doesn't have as big a non-polar side chain as the leucine does, so this is less non-polar than that one is. Then we have glutamine. This is an uncharged, but it is polar, so it doesn't have a net charge in it like an acidic or a basic amino acid, but it is relatively polar. And then we have lysine, a basic amino acid, which at this pH will be positively charged. So this is very polar. So what we have here is very non-polar, sort of non-polar, sort of polar, very polar. So let's think, as our solvent hits, as our mobile phase hits these molecules, they're going to move at different rates. So our leucine is going to spend more time in the mobile phase and will move up furthest. The glycine, again, is relatively non-polar, and it'll move up fairly far. Our glutamine is more polar. It doesn't have a very high affinity for the mobile phase, so it will move some way, but not very far. And our lysine, which is really polar, isn't interested really in getting dissolved in that mobile phase. That's hardly going to move anything at all. Meanwhile, the same thing is happening to our mixture of our amino acids in our dipeptide. So say, for example, for the sake of argument, if it were leucine-lysine, then the leucine would move the same distance as the leucine standard, and the lysine would move the same distance as the lysine standard. When you're done with the chromatography, you're going to mark with a pencil the solvent front, and then you're going to dry this whole thing out, and you're going to spray it with an anhydrin. As it stands, you can't see the amino acids, they're just clear colorless spots, but the reaction with an anhydrin will give you colored spots at the positions of the amino acids, so you'll be able to visualize where they are on the paper. And of course what you can do then is you can say, okay, well, I'm going to measure the distance of all of these spots, that's the RF value, and the RF value is given by the distance traveled by the spot over the distance traveled by the solvent front. That's why it's important to mark the solvent front. And what you'll be able to see is that you'll be able to compare RF values for these knowns and figure out, by comparing those with the RF values for the 2 spots in your unknown, you're going to be able to get the identity of the amino acids in your unknown.